So we're going to continue with our introduction into blood pressure with this video. And then from here, we're going to go into the barrel reflex, which talks about, or which is how the body maintains blood pressure. So we have these two outcomes for this video. So to start off, we need a few more definitions. So we need vessel diameter, which is exactly what it sounds like. So it's just what's the distance across the vessel, or it's twice the radius. Cross-sectional area. And so this one gets a little tricky and it's kind of hard to visualize, at least it is for me. And so just imagine that you took a very thin slice of a vessel and you measured the area of that vessel. Well, that's cross-sectional area. We're going to later on talk about total cross-sectional area, which basically just means, imagine if you just took a bunch of slices of each individual vessel, you took their area and then you added them up. That gives you total cross-sectional area. Then we've got blood pressure, which we've talked about. So that's just the force that's exerted on the vessel walls by the blood. And then we've got blood velocity. And so blood velocity is just how fast is the blood traveling. And so with the rest of this video, or most of this video, we're going to use a figure that looks like this one. The x-axis will be the same for all figures like this one. So notice that we're going from the arteries right here, all the way over through arterioles, capillaries, veins, and then we get to the vena cava. On the on the y-axis of this specific figure, we have vessel diameter. And so notice that diameter is really high in the arteries and even a little bit higher in the large veins. Okay, and so what we're going to do with these figures, with all these figures, we're basically going to divide them in half. So what's happening going from arteries to capillaries, and then from capillaries to the large veins. So as you can see from this figure, diameter decreases going from arteries to capillaries. Okay, because that diameter decreases, which means the radius decreases, if you recall from the previous video, small radius, large resistance. And so if we're just looking at this individual factor, just this one factor, resistance will increase as we go from arteries to capillaries. The opposite is true when we go the other way. As we go from capillaries to large veins, the diameter gets bigger, which means resistance decreases. Okay, remember, small changes in diameter have huge effects on resistance, because in that resistance equation we showed how radius is raised to the fourth power. So next we've got cross-sectional area. Okay, and so again, same thing on the x-axis. We're going from arteries down to capillaries and then up down to veins. And on the y-axis, we have cross-sectional area. And this is actually total cross-sectional area. Now notice that as we go from arteries to capillaries, the total cross-sectional area increases. Okay, and this is one we'll talk about in class, but can be difficult to wrap your head around. Okay, there are only a few large arteries. Okay, but there are millions and millions and millions of capillaries. And so you've got something that's really has a large area in these arteries, but you've only got a few of them. Whereas with capillaries, you've got something with a very small diameter, but you have millions and millions of them. And so if you add up all of the cross-sectional area, you actually end up with a really large cross-sectional area in your capillaries. And this is great for a variety of reasons. One, it reduces resistance. So as total cross-sectional area increases, resistance decreases. And this makes it easy for blood to flow through your capillaries. Similar to the last slide, we're just focusing on this one factor. Okay? When we go back from capillaries to veins, total cross-sectional area decreases, which means our resistance increases. Okay? So just to recap, capillaries have a huge cross-sectional area, and this is important because one, it means that that red blood cells and blood just generally doesn't have to travel very quickly through it, which allows time for exchange to occur. So this leads us into blood velocity. So again, x-axis, arteries to capillaries, capillaries to veins. Y-axis is the velocity. Notice that when we go from the left ventricle or the large arteries to the capillaries, velocity decreases. You have a low velocity, you have low resistance. A way to think about this is a river. Okay, if you've ever been river rafting, there are places where the river has relatively low velocity, and then there are places where it has high velocity. Generally speaking, high velocity are in the rapids. And when you're in the rapids, there's lots of resistance. That's actually what causes the increased velocity, because oftentimes you're decreasing the width across the river. And so you've got to force all of this water through a smaller area. Okay. When we go back into the veins, velocity increases. And so this increases resistance. Okay. Just think about those river rapids. Water doesn't just go straight through, it's bouncing all over the place. Okay. And so this slow velocity, like I said on the last slide, is important because it allows for exchange to occur. If the blood was moving too quickly, we wouldn't be able to have gas exchange or nutrient exchange occur at all, or at least not as efficiently. So this leads us to blood pressure. Okay, so in order for flow to occur, we need to have a gradient, which means we have to have, in this case, high pressure somewhere and a low pressure somewhere. So notice on this figure, again, going from arteries to veins, we have the highest pressure up here as blood comes out of the aorta into, or out of the ventricle into the aorta. And then by the time it gets to the vena cava, pressure is almost zero. Okay, this is important because it allows continuous flow of blood. We need that gradient. And so this gradient, high pressure in the arteries, low pressure in those great veins. We've mentioned before, arteries are elastic. They're like balloons. Okay, they expand to take on blood, but they don't like being expanded. So when the heart is relaxing and no more blood is being pushed into them, they recoil. Okay. Veins, on the other hand, are the exact opposite. They're more like paper bags. They're completely fine being stretched out. Okay, compliance is the opposite of elasticity. And so veins will expand to accommodate that extra blood flow, which means they can hold more blood volume. As a result, there's relatively low pressure inside the veins. So, as we've said, blood pressure, we need to have a gradient. We need to go from high to low. So we see that in this figure here. Arteries have high pressure due to elastic recoil. Veins have low pressure, but to help blood continue to move despite this low pressure, there are valves. So the skeletal muscle pump, and the skeletal muscle pump. Okay, and so the muscles actually will contract against the veins to help kind of push that blood forward, despite there being relatively low pressure. So at the end of this video, can you do these 4 things? Can you explain how vessel diameter, cross-sectional area, and blood velocity affect blood pressure? Can you explain how they change going throughout the systemic circulation? And these are just review questions from the previous video. Can you define pulse pressure? And can you calculate pulse pressure or mean arterial pressure given these values here?